Hello, everyone. In this week's Journal Club at Blue Spin Lab, I will talk about Canted spin texture and quantum spin Hall effect in tungsten telluride. It's a new strategy for spintronic applications, new material strategy for spintronic applications. And I will start with the current problems, why we wanted to do research on spintronics. It starts with the power dissipation. As you can see the scheme, and we have the current passing through the material, which is made of upspin electrons and downspin electrons. And we can say that it's the current in total is made of the current by the upspins and current by the downspins. So there's a power dissipation here. It's I times V. So the bigger the current is, the power dissipation will be huge. It's because the transportation of electrons is made by the scattering of charges, electron charges. So the main idea for the spintronics was the reducing it by using the magnetic scattering, spin scattering, and do not put charges in the scattering mechanism. So we can just assume that we have two currents with the upspins and downspins, and they are in the opposite direction. So we can use a current made of full of upspins and full of downspins, which makes the dissipation to do zero. This is a theoretical assumption. So we are talking about the controlling of the electron spins inside the material. To obtain this, we also need an efficient magnetization control by using different kind of techniques. So we are talking about injecting a polarized spin current inside the material. The main way to obtain this is a spin Hall effect. In the spin Hall effect, by using the spin orbit coupling of the materials, we are injecting charge current inside the material. And we see that in planary, perpendicularly, we have two distinct spin currents. It basically separates upspins and downspins inside the material. At the left, you see this mechanism in two ways. We send the charge current in one way, and we send the charge current in the other way. In both, we can observe the same mechanism once again. So at the right side, you see as a basic showing of the mechanism, which is the charge current made of two distinct spin states sending into the material, which is I think it's molybdenum telluride. It has a crystal structure, and inside this material there is a spin orbit coupling, and it separates the upspins and downspins. Then we will have a spin current. We can inject spin current inside the material. So spin orbit coupling is the most necessary for this mechanism, which creates the field of spin orbitronics. Now that we can inject spin currents with spin Hall effect, how about the transportation of information and energy? I mean, what happens to spins inside the material? As an example, we can show this video. I mean, if we say that Leonardo DiCaprio is our spin inside the material, we can see that its interaction with lattice, other electrons, other spins inside the material and during the transportation hurts our information and causes relaxation and dephasing. So there must be a way that we can actually protect the spin information and the energy of the spin due to this interactions inside the material. Losing information while transportation of spins inside the material by interacting with lattices and other components is a problem to be solved to achieve high performance spintronic devices. This requires some sort of protection of moving spin from the environment inside the material, which means that longer spin relaxation length. The longer spin relaxation length we have, the more accurate information we will be having into the device. So as you can see in this example, Conan O'Brien is landing into Japan and trying to move towards the crowd, and there's an escort moving with them to avoid any kind of interaction of him between crowd. So our goal to achieve is moving Conan O'Brien without any kind of interaction, without losing information to the place he wanted to be. Hence, we need a mechanism for spin protection. Has anyone invented something for this yet? Yes, and it's called the quantum spin Hall state materials. This is how it basically looks like. I will go deeper on this. So, at the right side, you're observing two different states. At first, at the upper side, you see blue line with up spin moving inside the material. It's called a helical state, which means that the material the spin is moving is basically an insulator at its bulk. But at the edge states, it has a conduction channel that makes the up spins move along. It's a helical edge state. While the spin is moving along, it has a magnitude of magnetic field B towards the upside. So vice versa, as an addition, it's moving counterclockwise. So when we go to the downside, the same mechanism happens for the downspin, and it has the corresponding magnetic field as well. So in the quantum spin Hall state, when we put them together, we see that magnetic fields are canceling each other, and we have two spin conductance channels moving towards the material. So we can actually create a healthy conducting line inside the material, which is a bulk insulator, but at the edge states, it has a perfect spin conductance channels. So for the cross-sectional area, you can see this view at the left side. And between these conduction channels, the area between them behaves as a quantum well. And at the outer side, we have the downspin conducting channels. And at the inner side, we have blue ones, the upspin charge carriers. So let's dig some more deeper at these kind of materials band structure. It will be a basic explanation of this. So at the right side, you see a band structure of the normal insulator. As you may know, to make an electron to be conducted inside the material, there must be an energy gap, which is possible to be achieved from valence band to conduction band. As the bulk insulator, when the entire sample is insulating, it's impossible for an electron to overcome this barrier. So when we look at the quantum spin Hall effect materials, we see that these bands are inverted. And at some point, the material acts like an exact insulator, but at some states, these bands are inverted and they are cutting each other at the Fermi energy level, as you can see in the square. The red and blue dot means those are the conducting channels of the spins. So quantum spin Hall materials act as an insulator in their bulk, but at the edge states, they can allow the spins to be conducted. So this sounds like a miraculous idea. We should mind the gap for those kind of materials. So how does this happen? This is basically conducted by the spin-orbit coupling. Here, it's a metallic energy band. You know, the conduction band and the valence band are just inside each other. It's a metallic behavior. So any electron can be transported from here to here. But when we apply the spin-orbit coupling, we are observing that the bands are being inverted, and there's an area between them are left away from the energy gaps, energy bands, which acts as an insulator. But in some certain points, we see that there's a perfect conduction points. This is how spin-orbit coupling affects the material. So when we apply the spin-orbit coupling, the system actually turns into an insulator with a topologically protected gap state. Topology here is named after the topology of the band lines, band gaps. Okay, so this is the motivation after the paper. As you can see here, there's an energy graph. Here lies an electron charge pocket. As you can see here, the It's just beneath the Fermi energy level, and the data you are seeing inside the little square is the model the writers of the paper is offering. This is calculated by the DFT for a very specific material, non-medium Telluride. And the main idea behind this is having the persistent spin texture in the charge pocket. Why is this necessary? I will be explaining this in the next slide. So, I also mentioned about the electron moving in the material and with its spin. So we know that there are lots of scattering mechanisms. So electron has this momentum. When the electron is being scattered, it loses momentum. And when it feels another magnetic field inside the material, it's being relaxed or it's being defaced for this kind of behaviors. So when we achieve the spin momentum locking, as you can see in the other picture, when all the spin texture is the same, it doesn't matter where electron is being scattered, it will be feeling the same magnetic field, and there will be no room for the dephasing or relaxation. So this can actually protect the information the electron carries with its spin through the whole material. And there is a mathematical explanation for this upside, which means that around the Fermi surface, the spin information is invariant from any kind of rotation, which is represented with u theta. This is a rotation operator in quantum mechanics. Okay, so we talked about the relaxation mechanism. So how about the spin Hall effect mechanism? We have been talking about the materials, and here the explanation of the type of the materials that we need to use to achieve those properties. So first, I will be talking about the symmetry, importance of the symmetry when we obtain the spin Hall effect inside the material. So at the beginning, you see how charge current is injected and spin current is being produced inside the material. So Mx and My represents the symmetry mirrors. They are mirror of symmetry, which means that there is a symmetry. And if there's a symmetry, there are points that you cannot have the spin have the information, spin have the direction. So at the first, we have 2 degrees of symmetry at Mx and My. And when we pass to the next one, we are just getting rid of the Mx symmetry mirror, and we will have only the My mirror. And as you can see at the red dots near the schemes, at first, we can have the spins only in the Sx, and only in the X direction. But when we get rid of the Mx symmetry, we will have Sx and Sy. We can have. And when we drop the latest symmetry, we will have 3-dimensional symmetry. This sounds confusing, but the main idea behind this is, if my material goes anti-symmetric as possible, I can have multi-dimensional spin Hall effect when I inject the charge current inside the material. So this must be the main idea inside the system to achieve. Imagine that you are sending charge currents in one direction and you are getting spin currents in multi-dimensions. This sounds pretty good for potential applications. So we talked about the symmetry properties. So mobilium Telluride was the perfect fit for the anti-symmetric properties. So how about the band gap properties that we mentioned before? Because as we talked before, like we need a proper band structure to obtain this insulating state. So this is how a DFT calculated mobilium Telluride band structure looks like. As you can see here, as the sad face, it actually looks like the offered in the model. There is a charge pocket here, but there's an intermediate pocket, intermediate band comes here, and it just harnesses the possibility to obtain a good quantum spin Hall material out of mobilium Telluride. So what is the alternative? Here, the same DFT calculations are made for tungsten telluride. And as you can see, there is the same charge pocket just beneath Fermi level, and there are no intermediate bands that can be harness the insulating state or the quantum spin Hall state properties. So this means that we can actually use tungsten telluride for our candidate for quantum spin Hall state material. So let's see if the model they have predicted for a charge pocket can work on this material. So the first idea was inducing the spin current inside this material. So there must be a computation for this. And they just simulated the situation for sending a charge current in the y direction and having the spin current inside the material of tungsten telluride. And the results can be seen here. The data is obvious. The three different data is coming from the spin accumulation in x direction, y direction, and z direction. And data is supported by the analytic calculations, which is, you can see here, at the downside right, you can see the amount of spin accumulation coming from y direction starts from 1 and drops to -1. And the amount of spin accumulation from z direction is coming from -0.5 and goes up to the 0.5. And at the x direction, there is no spin accumulation. This is the reason we have mentioned here. So there's a low symmetry material, and I can obtain two-dimensional spin current inside this material. I can have the y and z spin currents in the same time. This is also a really good idea. So at the left, we can see the spin Hall conductivity, spin Hall angle calculations for this material. This is called Berry curvature. And Berry curvature gives the idea about what is the exact energy range that we can have the maximum value of spin Hall angle. So let's see what do we have until now. So low symmetry materials to obtain multidimensional spin Hall effect is checked. Right compound, which is the tungsten telluride, to fit the model of two charge pockets is checked. Model and DFT calculations to achieve persistent spin texture is checked. So what we need then? Check if the spin Hall angle is feasible for the system or not. Check if the conductance is quantized or not. Check if the spin transportation is topologically protected or not. So the paper is based on these facts, proving those questions are right for the given material. So this is how they put the model into given material, tungsten telluride. It's the band structure and the DFT model. As you can see here, they could obtain the same band structure they offered for tungsten telluride. And by DFT calculations and their model, they fit each other, and they have obtained the persistent spin texture could be possibly obtained in this structure. Okay, here, this is the spin conductivity, and the thing I wanted to point out was where the phenomena happen, where we need to pay attention. As you can see here, the same domain here, where we have the charge pockets, the structure we need for quantum spin Hall effect, is where the spins are actually quantized. You can ask that, okay, there are two distinct values for those. Okay, so we can imagine that we can just assume that those spin currents are vectors. So one of them is moving in the y direction and one of them in the z direction. So for the magnitude of it, we should be doing a vector summation. So when we do the vector summation, we obtain the value of 2, which is the correct quantization for the quantum spin Hall effect. We have 2e² over h value for the quantum spin Hall effect of this material. When we look at the quantum, when we look at the spin Hall angle, the computation, they use the computational methods for that, it comes as minus 58 degrees. So this one is for the simulation of a 6-point Hall bar device, which they make the two different routes for a current inside the Hall bar, and to check if the values are quantized or not. So they have a theory and they have the simulation. They have the theory at the square lines, and they have the simulation values at the dot lines. So as you can see, once again, between minus 0.3 and 0 electron volts, they have obtained some sort of close to theoretical explanation. They have the protection of this spin current, and they said that since they are fitting in this domain, energy domain, we can actually assume that the spin current spins are topologically correct, topologically protected in this material. Since they fit at some point to the theoretical explanation, the simulation approves our logic is right. As a review back, low symmetry materials can produce the multidimensional spin Hall effect. You can create a persistent spin texture to avoid spin relaxation and spin dephasing around Fermi level. While transporting that spin current, it is quite useful to protect spin information with quantum spin Hall materials, which makes them quite useful for spintronic applications. Thank you.